Okay, what next? Let's look at what happens with the constitutive relations now. Now, if you ask most people what they understand by linearized elasticity or linear elasticity, chances are they are going to go straight to their understanding of the constitutive relations. Okay? So in the context of constitutive relations, linearized elasticity is so because you have a linear relation between stress and strain. Okay? Okay? All right. However, when approached more mathematically, one also recognizes that, well, an important component of the linearized part of linearized elasticity is this. Okay? And the implications that it has. Okay, anyway. All right, so how do we go about doing this? Since we're working with the Lagrange strain and we've started out by looking at things in the reference configuration, let's just stay there and let's consider the second Piola-Kirchhoff stress, okay? Let's consider the second Piola-Kirchhoff. Okay, and recall how this is done, right? We start out with by saying that psi equals psi hat of E, right, for our hyperelastic strain energy density function. And then we observe that yes, S is obtained now as this derivative. Okay? In order to bring out this linear aspect of linearized elasticity, or this other linear aspect of linearized elasticity, let us expand this in a Taylor series. Okay? What this means is that we get, and let's expand in a Taylor series about the reference configuration, which means E equals 0. Okay? Right? Which means if E is equal to 0, we know that we're still in the reference configuration, right? Okay. If E is equal to 0, we're in the reference configuration if we throw out rigid body motions, right? Because otherwise rigid body motions can also give us E equals 0. So let me just make that clear. Omega naught if no rigid motions. And if you recall what I did with the boundary conditions, just to fix ideas, indeed we can't have rigid motions with those kinds of boundary conditions, right? Because we fixed the displacement at the displacement boundary to be 0, okay? When we started out this exercise. Okay, so anyway. All right, so let's do that Taylor series expansion about E equals 0. What that tells us is that S is equal to partial of psi at with respect to E evaluated at E equals 0. Okay, plus the second derivative also evaluated at E equals 0. Okay, contracted with E. All right, plus the third derivative okay, evaluated at e equals 0. Now contracted with e, and I'm going to say contracted with e here as well. It's a little difficult to write this in direct notation without, it's a little ambiguous what this means in direct notation, because this object I've written here, the derivatives here, give us a sixth order tensor. Okay, but in fact, it turns out that that sixth order tensor has all the full major symmetries, so it doesn't really matter how we write this. Okay, if you want, we can write it out in coordinate notation, but I will write it out in coordinate notation in a minute. Okay, but anyway, and then you have higher order terms. Okay. So to be clear, let me state what we mean by that term. Okay. So okay, so this object with indices ij is the following. Okay, free index ij. Again, it doesn't really matter how we arrange those indices KL or ij or mn, because it has major symmetries. Okay, all right, we have that. However, what I want to point out is that now, because this object is already second order in E, okay, and we know that for displacement gradients that are small, it implies that anything that terms of order E square, right, which is what we have up here, okay, are much smaller than terms of order E. Okay, right? So what we are able to do is to say that S now is essentially, it's not equal, but it's written as that. Okay? Okay, that is our stress. Now, this term gives us the second pure law Kirchhoff stress about zero strain. Okay? If this term is, and this term is what we usually refer to as the residual stress. Okay? If the body without any deformation still has some stress in it, then this is it. Okay? But without any strain, if there is a stress in the body, then this is it. Okay? So this term is what we call the residual stress. Okay? All this means is that we've picked a reference configuration in which the body already has some stress from some process, right? Okay, it could very well be that we've actually deformed the body into the reference configuration and then chosen to relabel that. We've deformed the body into some configuration and then chosen to relabel that configuration as a reference configuration. Okay, and therefore the body has some strain and has some stress in it already. Okay, but then we're looking at strains from that configuration. So the way we've defined E, it could be 0. Or it could arise from other effects, right? Like there could be some certain defects locked into the body. Okay, things we're not going to talk about, dislocations or other types of defects can cause internal stresses in a body, okay, in the reference configuration. Or we could have thermal stresses. Or the body could be undergoing some processes that are tending to make it swell or grow. Okay, but we're not allowing it to grow. So there are many ways in which residual stresses can arise. Okay? All right, so we have a residual stress. Now, this term you should recognize as our old friend, the material elasticity tangent, evaluated at zero strain. Okay? As a result, it doesn't matter whether your constitutive relation uses the Samanon-Kirchhoff or not. This quantity is constant, right? We're computing the elastic tangent and evaluating it at a particular value of E, so then it's fixed, right? So this is constant. Okay? So clearly now, the stress is linear in E, whether or not we're using the Samanon-Kirchhoff model. Okay, so this thing is constant for any psi hat of E. Okay? So we see that what we have as a result is that S equals, let me be correct about this, let me use the approximation here. So S is plus a term C at E equals 0, right? Contracted with E, but E we're approximating as what? As this, right? Right? So we do indeed have a stress-strain relationship that is linear in epsilon. Okay? For for simplicity, let's just suppose that this term is 0. Okay? Okay, just for convenience. Okay, so now we have clearly S okay, nicely linear. Okay? So what I've been meaning to mention here is that for any model of nonlinear elasticity, okay, although we've demonstrated that this tangent is a constant, okay, so that holds, so we do have linear elasticity here. I should also say that the way nonlinear elasticity strain energy functions are written out, for any one of them, okay, when reduced to zero strain or when evaluated at zero strain, they all evaluate to the same quantity. Okay, so let me just state this here. So for all of them, right, even if we don't put down E equals 0, okay, sorry, no, when we do take them in the limit E equals 0, right, all nonlinear elasticity models, when you go and look at their material elastic tangent, right, they always evaluate to the same quantity, which is this one. Okay? So what this means is that all nonlinear elasticity models, when linearized about, when considered about zero strain, give us that tangent. Okay, the well-known constant linear elasticity tangent. Okay, so what this means is that all non-linear elastic tangents reduce to the linear elastic tangent at E equals 0. Okay? Of course, so this statement holds, but when I say that it reduces it to this particular form, this holds for isotropic materials, right? If the material were anisotropic, it would reduce to a different form, but then it would still reduce to the proper linear elastic tangent for that anisotropy. Okay, so this condition always holds. And I just noticed now that I've missed a transpose up here, so that should be there. Okay? All right. So we've looked at what happens with the kinematics and with the constitutive relation. We've seen the origins of the use of the term linear elasticity, right, or linearized elasticity. We've seen how it comes about in the kinematics, how it works its way into the stress-strain relations. Okay, we'll take a break here, and when we come back, we'll look at the balance of linear momentum.